Hello, Assalamu alaikum. Let's start a new chapter in our engineering mechanics dynamics course. The chapter is kinetics of particle, work, and energy. In the previous chapter, in chapter number 12 and chapter number 13, we discuss about the kinematics and kinetics. In chapter number 12, we discuss about displacement, velocity, acceleration, and time. Whereas in chapter number 13, we discuss about the forces acting on a particle. Those forces were acting on the particle which is moving in a straight line, as well as which is moving in a straight line, as well as which is moving in a curvilinear path. Or we also discuss different coordinate systems which were cylindrical coordinate system and Cartesian coordinate system. In chapter number 14, we will be discussing a very important aspect of motion and dynamic of a particle, which is work and energy. From your elementary classes, you might have a very good idea about work and energy and what are the units and how to calculate the work and energy. And in this chapter, we will be discussing in detail about the fundamental concept of work and energy, and we will be applying the equations of motion and Newton's second law of motion in order to calculate Newton's second law of motion and the work energy equations to calculate the different work energy of bodies moving with certain velocities and undergoing velocity changes and having acceleration. So let's begin with the chapter. First of all, what is a work? Work done is basically work happens when you have a body having some mass, and when you apply force, it covers some displacement. Here we have a box shown here. If you can see my mouse, this is the box, blue box, and on which the force is applied vertically downward. So logically speaking, like there will be no motion of the box. You can see that there won't be any motion. But if you apply a force at a certain angle, you will see this ds. From now we will be discussing the displacement, as we already discussed the displacement in chapter number 13 and 12 and in terms of s. तो यहाँ पे आप ये देख सकते हैं कि जब आपके पास फोर्स अप्लाई होती है और फोर्स जो है वो सर्टेन एंगल पर अप्लाई हो रही है एट विद हॉरिजॉन्टल, that force has two different components, Fy and Fx. So यहाँ पर पार्टिकल की डिस्प्लेसमेंट पोजीशन थी और कुछ देर बाद वो पार्टिकल जो है वो कुछ दूर ds पर पहुँच गया, यहाँ पे ds से पहुँच गया. So this actually shows that it covers some distance and by the application of the force. So this is actually the simple definition of work done. Let's talk about a particle which is moving in a curved path. यहाँ पे you can see the blue line which is showing the path, which is represented by s. That similar concept when you have a particle which is at a location defined by a unit vector r, and after some time the particle moved from position 1 to position 2, which is now represented by a new unit vector r dash. So the difference between these two vectors is dr. This is the same thing which we discussed in our previous chapters. So similarly, along this path, the position of the particles from point 1 and point 2 is changing, and the arc length with the, or you can say the distance covered by the particle from point 1 to point 2 is represented by a small differential distance ds. This happens because there is a force acting on the particle at a certain angle theta. So I can just give you a recap again. You have a particle, and the particle is subjected to a force which is making an angle theta with the horizontal, or I would say the tangent, and this distance from point 1 to point 2 or the position which is represented by r and r dash are represented by this line, this vector line, right? So the angle is theta. So from this equation, work done du, we will be representing the work done as u. The work done in this chapter, the nomenclature to represent work done is u. So the differential work done from the position r to r dash is denoted by du equals to f cos theta. So what is f cos theta? Because f is acting at a certain angle, the component of the force which is acting along the direction of the motion will be f, and the f times cos theta, which is the component along the direction of the motion, and ds is the displacement from point 1 to point 2, or point r to point r dash. So this is a pretty simple formula, and I guess this is the formula which you have encountered multiple times in your elementary or elementary classes, in your initial classes. So moving forward, similarly, if you can see closely, the relation f cos theta ds is nothing but it's a dot product of dr and f dot. F dot and dr. F is the force and dr is the small. It's at a difference between the vectors r and r dash. So f dot dr is basically the burden in the vector form. This is a dot product of two vectors f and dr. Dr is the difference of the vectors r and r dash. You can see from this triangle, or this triangle, that r plus dr is basically r dash, or in other words, r dash equals to dr plus r1 r, right? So this is this is actually the old knowledge which you have already discussed, which you have already covered in your previous classes. Moving forward, now the things becomes a bit complicated. What is happening? So far in your previous classes, what you have done, you have only covered the forces which were constant. Now let's talk about a force which is a variable. For example, if you have a force, if you have a path which denoted by a line, blue line S, and at certain there's a particle which is moving along this path, and the force F is acting on it, and so you must be aware by now that the only component which is responsible for the work done is the cos theta, the cos component of the force, which is along the direction of the motion, right? So which means that if the force F cos theta is changing along this whole curve, blue line, with certain so you can say that variable of variation of the force is represented by this graph. So on the x-axis you have s, which is representing the position of the particle, whereas on the y-axis you have f cos theta, because why f cos theta? Because we are only concerned with the cos component of the velocity of the force. We are not concerned with the y component, or simply f, because this is the only component which is responsible for the work done. Now, so f cos theta is changing along the curve path s, and which is represented by this curve, right? So at s1 and s2 you can see there's a graph which is showing the variation of f. So if you can see, if we want to calculate the work done u from point 1 to point 2, 1 dash 2 is, so which means we need to integrate f dot dr. What is f dot dr? This is a vector form. So in order to understand it rather in a simpler way, we can see the scalar form. So you can see that s1 is the lower limit on the x-axis. So if I need to find the work done by this force, this variable force from s1 to s2, I just need to find the area under the curve. Area under the curve of this curve, this line, blue line, right? So what is happening here? What is happening that we have s1 and s2, and we have s1 and s2 at the lower and upper limit. We have f cos theta, which is a function of s, which must be a function of f, and we have ds. Ds is a small differential distance which is being covered along the path. So when you simply use this s1 s2, what would happen? We can simply f cos theta must be a function of s, and ds is the small differential displacement along the x-axis, and s1 and s2 represent the lower and upper limit of the displacement. So by using this relation, we can find the variable by the work done by the variable. Now let's talk about, now let's see what happens when you have a constant force. When you have a constant force, that's a pretty simple solution. We have a particle which is moving in a straight line from s1 to s2, and we have a force Fc acting at an angle theta. So simply we took the cos component of the force and we are multiplying it with the range of displacement. So graphically it is very easy to understand. We have a force which is constant. Fc is representing the constant subscript. Cos theta is the relevant component of the force, which is actually constant throughout the whole journey of the particle from S1 to S2. So if I calculate the area under the curve of this line, so that is pretty obvious. This will be simply a rectangular area. So the f cos theta times S2 minus S1, which is the distance between these two lines, and hence the rectangle. So the we can use the same relation of integrating the f cos theta function along the limit S1 and S2, but you can see that when you have f cos theta as constant, you can take out this term out of the integral and simply integrating it with respect to ds and by applying limits for S1 and S2. That's a pretty simple one, right? So just to sum up, when you have a variable force, you need to integrate it, and the force should be a function of s. And if you have a constant force, you simply use f cos theta times delta s. Now moving forward, let's discuss about the work of the force of gravity. So what happens when you have a particle moving in a path and the weight of the particle is dragging it down? So let's see, let's just see this graph. We have a path which is represented by s. We have a position s1 and we have a position s2, and a particle is moving between these two particles. The s1 is represented by a vector r1, whereas the s2 represented by r2, and we have a weight acting or dragging the particle downwards, right? So if I apply the equation of the work, f dot dr integration from point 1 and point 2, so the force acting on the particle is basically the weight, and in terms of the Cartesian vector form, minus w j is the vector, the unit vector along the y-axis, so minus representing because it is downward, dot the position of the particle at dx, dy, and dz and dzk, right? That is showing the differential displacement along x, y, and z axis, right? So we know that we have to find the work done by the force of gravity, so we are not concerned about the other two axes, which are z and x, since the force is acting along the y-axis. Otherwise it would be changed in case of the force, the w is acting in other axis, but in this figure particularly the force is acting along the y-axis. So we have, if I simply use the limits as s1 and s2, at s1 we have y1 and s2 we have y2, so minus w dy. How we come up with this relation? Because when we apply the dot product, the j dot j is coming out to be 1, whereas j dot I 0, j dot k is 0. This is the basic vector mechanics you are all familiar with. So minus w dy, and because w is constant of the constant, so dy, when you apply limits to dy, we get y2 minus y1. So you can see that the work done by the force of gravity is very simple, minus w delta y. Minus w is basically showing that the fact that the displacement, if the vertical w is acting downward, and if a body is moving upward, the work done is negative, as the gravity will oppose the movement and vice versa. So and the displacement value or displacement term is simply the difference between the final position and the initial position. So in order to understand, this is pretty simple, right? So let's move forward. Let's talk about the work of a force exerted by a spring. This is again the concept which you have covered in your previous classes. We have a spring. When we apply a force Fs, S representing the spring force, and so we know that the displacement, the force is directly proportional to the displacement, and we have a K, which is the spring constant. So when you stretch a spring, what would happen? The restoring force, which is in the opposite direction, when you are stretching it, you are actually elongating the spring, you are increasing the length, and the restoring force is opposite to the direction of the force, which means the displacement and F are in the opposite direction. Vice versa, if you are compressing a spring, you are applying a force against the spring restoring force. The restoring force is against the direction of the displacement or the change of length, right? So you can see that if I need to find the work done by the forces of the spring, u, which is the work done, 1 minus 1 dash 2, which is the position 1 and 2, is fs is the spring force and ds is the displacement. So same relation s1 to s2, but here we have fs as equals to minus ks. Ks is the spring constant and ks is the displacement, to find displacement of the spring which is being reduced, right? And ds is the s is the initial s is the value of the displacement, whereas ds is the change of displacement, right? So when you integrate it, minus sign is if the particle displacement and spring force are in the same direction, hence positive work result if they are opposite to one another, the work is negative. So actually in generally we need to have this minus sign because of force, and when you are elongating it, although you are stretching it, you are increasing the length, but the force is in the opposite direction. So when you integrate this relation with being k as a constant and as ds is the variable, you can find this relation as pretty simple integration, 1 upon 2 k s square as k s 2 square minus 1 upon 2 k s 1 square. So this is the relation for the work done by the spring. So when we will be solving numerical, you can get a better idea what we are talking about, because this theoretical part is just to give you an addition, to make your foundation, and then we will be solving some numericals as well. So moving forward further, let's just have a summary of everything which we have discussed so far. Variable force, we have x-axis, on x-axis we have f cos theta, we have on y-axis we have s, which is the path being followed by the particle. We integrate f dot dr in the vector form where r1 and r2 the limit, but in order to in the scalar form we have f cos theta ds, where f cos theta should be a function of ds displacement, and we can apply s1 and s2 the position of the particle at initial and final position to calculate the work done between these 2 points. Similarly, that's a pretty simple one. When if we need to find the particles were then subjected to a constant force, so we have fc cos theta simply multiplied by the s2 minus s1, which is the change of displacement or the change of the position. Thirdly, we discuss about the if an object is moving upward, the work done is negative as the gravity will oppose the movement, and vice versa. So which means that if the work done on a particle by gravity is nothing but the product of delta v in times w. Delta v could be delta z or delta x depending upon where you have your axis placed, right? So that's not a problem. Thirdly, the last one is the spring force. Spring force, the work done by the spring force, we have k as a constant, as a spring constant, which will be provided to you, whereas s2 and s1 are the initial and final position of the spring. Minus sign only shows that the forces are forces exert in the opposite direction of the displacement. So moving further, let's talk about principle of work and energy. This is a very important topic to discuss. First of all, let's discuss about the problem. The figure. We have a path shown by a blue line where we have point 1 and point 2, and the particle is moving in this straight line, right? In this on this curvilinear or this curved blue line, right? At certain point, the particle is subjected to a force Fr, which is a combination of multiple forces. Here, in just like the previous chapter number 13, we have a force which is along the tangential direction, and we have a force which is along the normal direction toward the center of the radius of the curve. So we have two forces, Ft and Fn, but in a real world, in a real problem, this particle might be subjected to multiple forces, and that Fr is basically the summation of all those forces. So we have tangential component here delta Ft, we have delta Fn, the normal component delta sigma representing all the forces which are acting in the n direction, and sigma Ft representing the forces along on the tangential direction, and Fr is the big Fr, which is the sum of all the forces. So now the particle is moving in this path, and we have point 1 and point 2, and the small displacement ds being covered by the particle, with the velocity v. So this is the actual figure of a particle. Now let's see what is going on. We have, since the motion is along the tangential direction and the work done is along tangential direction, because there will be no movement along this axis. So although there is a force acting on it, but the movement, there is no movement or there is no position change along the normal direction. So there will be no work done along n. So we are only concerned with the work done along the tangential direction or the direction along the curve, because there is no ds along n, right? So we have ft, which is the tangential force, is equals to mass time acceleration along the tangential direction. We know that at is basically equals to at ds equals to v dv, where ds is the displacement and v dv is the velocity and differential velocity. By substituting, we have by moving ds to one side, we have at equals to v dv upon ds, right? So if we replace this at into this equation, which is equation number 1a, we have this equation, which is f equals to m times acceleration at, right? ft equals to m times at. So exactly right, we have 80 here, and we just simply replace it in equation number a. Now now if I need to find the work done, so we need to multiply with the ds on the both side. So ft ds equals to m dv upon ds. Now we multiply it with ds, so ds cancel out each other. Now we have this equation. So if I integrate this equation, what would happen? Integral s1 to s2 ft ds, this is the total work done by the force which is along the tangential direction, is equals to mass time integral v dv. So this is a non-linear function. This is linear, and when you multiply it, it becomes a quadratic function, right? So you can see that this equation is converting into a quite familiar relation, which is half mv2 square minus half mv1 square. So this total work done is basically equals to the change of that. This is a relation of kinetic energy, if you remember, half mv square. So let's see what's the physical meaning. So here we have, this is the total work done. This is a total work done on the particle in the form of force acting on the tangential direction and the displacement along the s direction. We have m integral m, because this is a relation coming from this side on the right hand side, and which gives you this relation, which is half mv2 square minus half mv1 square. If we just move these relations from one point, like, okay, let's give some name of them. This left hand side is basically equals to the summation of all the work on the particle from point 1 to 2, and the first term is basically t1, the initial kinetic energy, and the second term is the final kinetic energy. So if I just move first term to the right hand side, you will see that the initial kinetic energy plus the work done on the particle by all the forces acting on the body, resulting in the final kinetic energy of the body. For example, if a particle is moving and suddenly because of motion, there's a velocity and there's a initial kinetic energy, and suddenly after you apply some forces on it, and that forces do some work on the particle, that is the work done by all the forces, and after when you sum the work done and the initial kinetic energy, you will get the final kinetic energy of the particle. So this is called the principle of work and energy. This is a very important relation, and we will be using this relation quite often in our following numericals, inshallah. Now let's see an example from the book to understand the concept which we have covered so far. This is a very good example to apply all the relations, all the concepts which we have covered so far, except the fact that the force acting on the particle is constant. Now let's see how the problem goes. A 10 kg block shown in the figure rests on the smooth inclined surface. If the springs originally stretched 0.5 meters, determine the total work done by all the forces acting on the block when a horizontal force P equals to 400 Newton pushes the block up the plane 2 meters. Now first let's see all the forces acting on it. We have a force which is there's a plane which is horizontal making an angle 30, which is a plane which is making an angle 30 with the horizontal. We have a block which is 10 kg attached to a spring. Initially the position of the block is at this point, which is 0.5 from this wall. The K is given by 30 newtons per meter. What is happening? We have a force acting on it which is horizontal, which is not making an angle but it is horizontal, and that force pushes the block to a new position which is 2 meters from the initial position. The initial position was 0.5 and the final is 2 from the initial, right? So it is not the total is 2.5 actually. So now the initial position is here. So initial position's vertical distance from the final position is 2 sine 30, because this is 2, and the horizontal is 2 cos 30. Now, so how many forces are acting on it? First of all, first force is P, which is the external force. One force is the weight of the box, which is 98.1, the 10 times 9.9.81. We have a spring force which is resisting the motion, Fs, and we have normal force because the box is placed on the surface, right? Normal force. Now we have to find the total work done by all these forces. So we have one force weight, we have force P, we have force Fs, and we have normal force NB. So we have 4 different types of forces which are acting on this body, and now we have to find the work done, total work done by all these forces. So now move on to the numerical. So first of all, let's first discuss the horizontal force P. So as you can see from the figure that the UP, the work done by the P, is basically 400 times 2, which is the this horizontal distance cos 30, because because we need to multiply with the x component of the displacement 2, or vice versa. What we can do, we can multiply, we can use the x component of the force and multiply it with the displacement. So that doesn't make any difference, right? So you simply, it is 400 times 2, which is the displacement, times cos 30, which is the angle between that's the easier way to calculate, intuitive way to calculate. So 400 is the force, 2 is the displacement, and cos 30 is the term which comes from the relation, right? They're coming out to be 692.8 joules. This is the work done by the horizontal force. Now moving towards the spring force. In the initial position, the spring is stretched. S1 is 0.5 as mentioned in the question, and the final position is S2, which is 0.5 plus 2, because initial plus final is 2.5. We require the work to be negative since the force and displacement. So right, so we have the US, which is the spring work, minus 1 upon 2. 30 is the K value, 2.5 is the final value, and the initial value is 0.5. Because this 2.5 is taken from the from your reference point, right? So you should be very clear, very careful about as to it cannot be 2, right? This is 2.5 minus half 30, and 0.5 is the initial position, so we are getting minus 90 joules. So the work done by the spring is negative because you are pushing it, and the spring is basically resisting the motion. So this is quite understandable that the work done by the force is pushing it, while the spring is resisting the motion. So the spring is doing a negative work on the body. Now let's come to the weight part. Weight is acting downward. So because there is a sign component of the displacement S, so that is the V part, delta Y part, minus 98.1 times 2 meters, which is the displacement, times sine 30, and that is delta V. So the UW, the work done by the work done by the weight, is basically minus 98.1 joules. Now the last word was normal force, and since there is no motion along the normal direction of the plane, so there is no displacement, hence there will not be any work along the normal direction of the plane, so there will be no work by the NB. So hence the total work done is by the force P, which is positive, by the spring, which is negative, and by the weight, which is also negative. So the total work done by the box is 505 joules, and that is an answer. So from this formula relation, we got to find that the particle on a body might undergo a total burden, which is a result of multiple forces acting on it, and might be the burden by some of the forces are zero. In this case, that force is the normal force, right? So in the next class we will be solving more numerical related to this topic. Thank you very much for listening.